Right, welcome ladies and gentlemen. Now this is the video where I'm going to go through some additional examples of calculating K values from concentration, but it's going to be specific to Ka problems. I'm going to touch on Kb problems and then specific to KSP problems. So if you feel like you get the general idea and you see how this could apply to acid-base chemistry and to solubility chemistry, then maybe you just skip through this or look at a few of the slides. But if you feel like you could use a couple additional examples, then this is what this is. So this should be the second video on this topic that really just goes through a couple extra problems about the process of calculating K from concentration. So this is our second primary topic of equilibrium. Now we're starting with a repeat slide. There are always three basic steps to equilibrium problems, sort of regardless of whether it's getting K from concentration or concentration from K. Because this is going to be the basis for all the problem-solving work that we're going to be doing, the questions that I go through later. The first thing that you want to do, if it's not given to you in the problem, you need to write a reaction. That always should be our most sort of fundamental instinct. We need a reaction so that we can understand what's going on. Maybe it's neutralization if it's titration, maybe it's acid dissociation, maybe it's base dissociation, maybe it's a solubility dissociation reaction, but you need to write a reaction. Then you need to fill in an ice chart as much as possible. There should be something written in every spot in the ice chart, so it needs to be filled in. Then you're going to, once you've filled in your ice chart, then you go to the K expression. You write your K expression, you plug in the values from the ice chart, and then you calculate whatever it is that you're trying to solve for. So making this specific to Ka, calculating Ka from pH. This is an extremely common type of question in chemistry, especially in AP chemistry. This type of question has been all over the AP chemistry exam in recent years. This should feel very comfortable to us by the end of this particular unit. So sample problem, the pH of a 0.1 molar solution of formic acid, HCHO2, was measured to be 2.38 at 25 degrees Celsius. Calculate Ka for formic acid. So we're going to use the three steps, the three main steps for doing any equilibrium problem. The first thing that we want to do is write a reaction. So we kind of have to think about that. Well, what reaction are we going to write? They indicate that they want us to get Ka, which means that there is no base in this solution that the formic acid is reacting with, which means that we want to write an acid dissociation reaction. That's all we have. We have formic acid and that's it. So your reaction is your Ka reaction, your acid dissociation reaction. So that's the first thing that we want to do if we're not given a reaction. So acid dissociation reactions, as a reminder, they simply show acids behaving as acids. So we've got HCHO2. Now this is acid dissociation. So it's going to split into H plus and CHO2 minus, right? The H plus and then the other stuff, the whole rest of the acid. So that's the reaction that everything is based off. That's step one. Step two, we want to fill in the ice chart. So here's where the math is going to come in. ICE, remember we're using molarities in our ice chart. Here's where we have to interpret the problem. The pH of a 0.1 molar solution of formic acid was measured to be 2.38 at 25 degrees Celsius. So this number right here, the 0.1 molar. Reading and interpreting the problem, 0.1 molar solution of formic acid, the HCHO2. We know we're dealing with the HCHO2, not the H plus, not the CHO2 minus, just the HCHO2. The 0.1 molar solution, that's your initial. This person made this solution of formic acid to start out as 0.1 molar. So if you're given a concentration of a weak acid like this, that is your initial concentration. So I'm going to plug in the 0.1 molar here. Now, the other number that we have, well, first of all, we have temperature, the 25 degrees Celsius, but that doesn't enter into our ice chart because it's not a molarity. The other number that we have is 2.38. That's the pH, right? The pH of this solution was measured to be 2.38. That's a critical number for us because we're going to use that to get other things that we're going to put into our ice chart. Now, pH, by definition, is the negative log of the hydrogen ion concentration. So recall that if you do 10 to the negative pH, you get your hydrogen ion concentration, which is exactly what we're going to do here, 10 to the negative 2.38, to get our hydrogen ion concentration. I give you pH. Hey, look at this. We've got H plus that's in this reaction. You're going to use that pH to get H plus information. So if you do 10 to the negative 2.38, which you should, please, we get a hydrogen ion concentration of 4.2 times 10 to the minus third molar. But then the big question is, where does it go for H plus? We've got this hydrogen ion concentration, but is it initial or is it equilibrium? That's where you have to understand how the problem is interpreted. We made the solution of formic acid at 0.1 molar, so that's the initial concentration. Then we measured the pH. pH, this thing right here, you did not start by adding any hydrogen ion on its own into the flask, meaning the hydrogen ion concentration actually started at 0. And then it dissociated, then the formic acid dissociated and created this 4.2 times 10 to the minus third molar hydrogen ion concentration. When pH is given to you, or POH is given to you in a problem like this, it is telling you the equilibrium concentrations, not the initial concentrations. So I'm going to take that 4.2 times 10 to the minus third, and that is my equilibrium concentration of the hydrogen ion, meaning I started in my flask before I put the formic acid in with no H plus. So initial concentration of H plus, 0. Then I added my 0.1 molar formic acid. It dissociated and created something that had a pH of 2.38. So the equilibrium concentration of H plus is 4.2 times 10 to the minus third molar. From these three values, we have enough information to fill in everything else in the ice chart. Recall that all the products start at 0, so the formate ion is also starting at 0. Now we can fill in the change for the hydrogen ion because, you know, how do you get from 0 to 4.2 times 10 to the minus third? Well, you have to add 4.2 times 10 to the minus third. Then you're going to use stoichiometry, use the molar relationships to take the change that you see in the H plus and apply it to the change for the formate ion and the change for formic acid. It's real easy here because everything is 1 to 1 to 1. So if I generate 4.2 times 10 to the minus third molar hydrogen ion, I will also generate 4.2 times 10 to the minus third molar of the formate ion, meaning I will have that as my equilibrium concentration there. Then, looking back at the formic acid, again, it's 1 to 1 to 1, but remember that you need to subtract your reactants. Your reactants are getting used up. It's the same value because it's the same molar relationship. 1 mole of formic acid creates 1 mole of H plus. Doing the math that it says to do, 0.1 minus 4.2 times 10 to the minus third, we get 0.0958 molar for the equilibrium concentration of formic acid. See how this is exactly the same? I mean, the slight distinction is that you have to start by working with pH and understand that that pH is the equilibrium H plus concentration. But in terms of filling in the ice chart, this is absolutely identical work to the previous examples that we went to. Now that we filled in the ice chart, we're on step 3 of the 3 things that we do. We wrote the reaction, we filled in the ice chart, now we're going to go to the K expression and we're going to plug in. So writing that K expression, Ka products over reactants raised to their coefficients. So we're going to do H plus times CHO2 minus, these are all raised to the first because the coefficients are 1, divided by HCHO2, and then plugging in from the equilibrium concentrations in the ice chart. So we're going to do 4.2 times 10 to the minus third, and I'm just going to write that out as squaring it because it's this times this. They're both the same, so it's just 4.2 times 10 to the minus third squared, divided by the formic acid, 0.0958, and then it's just doing math. It's solving for the K value. When you do that, which I would like you to do, pause the video, get a Ka value of 1.84 times 10 to the minus 4th. Now this is a very common magnitude range for Ka values. Ka values are pretty small. They usually start, the largest of them start at around 10 to the minus 3rd, and they go to about, the ones that we tend to see, 10 to the minus 8th, 10 to the minus 9th or so. So they are small. They are small in number. And they're small in number because what they're saying is this ratio between products and reactants, where products are on the top in the fraction and the reactants are on the bottom, we're getting a number that's less than 1 by a lot. It's fairly significantly less than 1 because if you look at your products versus your reactants, you've got way more reactants. Your products are kind of weak and piddly and limping along in small amounts, but you still have a lot of your reactants. So this is saying, when you've got a K value that's less than 1, that you have more reactants than products when you're at equilibrium, that this system, when it reached equilibrium, it only had the 4.2 times 10 to the minus 3rd molar H+, but it still had quite an awful lot of the HCHO2. That's where that percent dissociation is really coming from. It's saying that, oh, hey, look, not a lot of that H+ dissociated off of the formic acid. And we can calculate, the amount that did, but we see that it's significantly less than what we started with. Now, calculating Kb from pH, I'm not going to go through the math on this example. I'm just going to kind of talk about it and set it up. Calculating Kb from pH information is virtually identical to calculating Ka from pH information. There are just a few crucial little changes, but they're changes that you already know. So it's nothing new with the equilibrium concept. It's basically just about realizing that, okay, if we've got OH minus and we're given pH, we have to do one additional step of math in order to go from pH to hydroxide information. But it's all linked, and it's all stuff we can already do. So just as an example, I'm going to kind of set this up. I'm not going to go through and actually do this problem. How would this problem sound? Calculate the Kb value of an unknown base whose 0.01 molar solution has a pH of 8.75. Now, this information is virtually identical to the information that we were given in the previous problem. Where it's going to differ in terms of the work that you're doing. You're asked to find Kb, meaning you want to write a base dissociation reaction. So your base dissociation reaction, as we recall, is B for our random base. You have to add water to it. And then we are generating the conjugate acid of the base and the hydroxide ion. And when you set up your ice chart, for the Kb reaction, for the base dissociation reaction, remember that water is a liquid, and we do not put liquids into our K expressions because their concentrations don't change. We don't talk about liquids concentrations changing because they're pure substances. They're 100% of the same thing. So you sort of cross off the water from your ice chart calculations. And then that 0.01 molar, that would be the initial for the base. We're starting at 0 for both of the products. This pH of 8.75, we need hydroxide, right? Because we've got the hydroxide here instead of H+. So we're going to go from pH to OH minus. And whether you want to do pH to POH and then 10 to the minus POH, that's fine. If you want to do pH to H+ to OH minus by the Kw relationship, then that's fine too. But know that this thing right here, once you get that OH minus, it will go into the equilibrium slot on your ice chart, not the initial. So it's incredibly similar, with the only changes really coming from acid-base stuff that you can already do. You write a base dissociation reaction, which needs to include the water, but that's not part of the ice chart because it's a liquid. And then we need to take the pH to the hydroxide concentration rather than just the hydrogen ion concentration. Really, everything else beyond that is identical. And then the last example that I want to go through is doing this type of equilibrium problem, determining K from concentration, in the KSP manner. So that other sort of flavor of equilibrium reaction. And so you can see what it looks like there. So calculating KSP. Saturated solution of silver chromate is prepared where the silver ion concentration is 1.3 times 10 to the minus fourth molar. Calculate the KSP value assuming the solution is at equilibrium. They actually didn't need to include that last portion of the last sentence, assuming the solution is at equilibrium, because they've actually already told us that it's at equilibrium right here. By telling us that the solution is saturated, it actually means that the solution is at equilibrium. That's a huge indication for us that we are in fact dealing with this solubility equilibrium. Unsaturated solutions are not yet at equilibrium. Saturated solutions are there. So we want to follow, again, the same set of 3 steps. We want to write a reaction, we want to fill in an ice chart, and we want to plug into the K expression. But the reaction that we're writing now has changed. We're dealing with silver chromate. They're asking about KSP, so we want to write a KSP reaction. KSP reactions are about solubility. It's about taking that solid silver chromate and it's dissociating into its ions. What are the 2 ions in silver chromate? How about silver and chromate? That's what it splits into. But you have to pay attention to the subscripts. So it's Ag2CrO4. Therefore, it's going to split into 2 silvers, which are aqueous, and the chromate ion, which even if you don't remember the charge, you should be able to figure out because silver is +1, and I did ask you to memorize that, which is 2 minus. So that's the reaction. That's what all KSP reactions look like. You've got your solid, and it splits into the 2 ions, which are aqueous. We want to fill in an ice chart. So that's step 1 down. Next step, fill in the ice chart. Same process, same exact process, just applied to a slightly different type of chemistry. Now, for filling in the ice chart here, things are slightly different because, oh, looky, looky. Oh, look at that. Oh, we have a solid. You do not put solids in the equilibrium expression because their concentrations do not change. And if you do not put solids in your equilibrium expressions, it means that you don't need to calculate anything about the solid. So you cross it off. It's not going to be a part of your equilibrium expression. Therefore, it is not a part of your ice chart. So we're going to focus instead on just the products. Initial concentrations of the products. Does this problem tell us that before we put the silver chromate into solution, that there's any silver or chromate already there? No, it does not. That number for the silver, the 1.3 times 10 to the minus fourth, is for the saturated solution. A saturated solution was prepared where the silver ion concentration was this. The saturated solution, the fact that they use that word saturated, that means equilibrium. So that number right there, the 1.3 times 10 to the minus fourth, that is not the initial concentration of the silver. That is the equilibrium concentration of the silver. So I'm going to fill that in there. They said that, hey, we dissolved some silver chromate. We let it get to equilibrium. We then looked at it, and we figured out that the silver concentration was 1.3 times 10 to the minus fourth molar. That is the equilibrium concentration, not the initial amount of silver that was already hanging out in the water before they added the silver chromate. Which means that it started at 0. And as there is absolutely no discussion of chromate anywhere, we also know that the chromate starts at 0. This is the same stuff. This is the same set of processes. We can figure out then that the change, how do you go from 0 to 1.3 times 10 to the minus fourth? You add 1.3 times 10 to the minus fourth. Now we're going to use stoichiometry to apply the change from the silver to the change for the chromate, and that's based on the mole ratios. Silver and chromate are in a 2-to-1 molar relationship, meaning you generate twice as much silver as you do chromate. Right? That's what that's saying. For every 1 mole of chromate, you get 2 moles of silver, which means that the change for the chromate is going to be half that for the change for the silver. Convince yourself that this is true. Set up an ice chart. Set up a T-chart, excuse me. Use the silver concentration, then use the coefficients. If you start with the 1.3 times 10 to the minus fourth, the 2 moles of silver is on the bottom, the 1 mole of chromate's on the top. So this is going to be plus half of the 1.3 times 10 to the minus fourth. which is 6.5 times 10 to the minus fifth. We have now filled in the ice chart as much as we possibly can, which means our next step of our 3 steps, write a reaction, fill in an ice chart, go to the K expression, is the K expression itself. So this is the KSP, products over reactants raised to their coefficients. So it's going to be the concentration of the silver ion squared times the concentration of the chromate ion over a big old fatty 1. Do not put the solid into the equilibrium expression. They don't go there. It's only aqueous things and gases that go into your equilibrium expression. So that's it. That's your equilibrium expression right there. Plugging in then, we're going to do with 1.3 times 10 to the minus fourth. You always plug in your equilibrium line from your ice chart, the very last line, times 6.5 times 10 to the minus fifth. And then it's just solving, it's just multiplying these values together. And when you do this, you get a KSP value of 1.1 times 10 to the minus 12th. Is that very small? Yes, it is very small. That's why silver chromate is considered insoluble, because you put it in water and a very small amount of it actually dissociates. KSP values are even smaller than Ka values, generally speaking. They tend to start at around 10 to the minus 8th and go even lower, on the order of like 10 to the minus 15th. That's usually the range that we'll see them in, but they can be lower, they can be higher, but those are really the common ones. So you expect to get a very small number here, meaning that we don't have a lot of silver ion or chromate ion in solution because it's insoluble. Not much of it dissociates. That's why it's called KSP. So these are a couple extra examples that will hopefully help you when you look at the problem set in class.